ever really stopped and thought about like how we learn from messing up?
Right.
It's like we just do it, right? Almost like second nature to us humans.
Right.
But what about machines? How do we get a computer to learn and adapt and like improve just like people do?
Yeah.
That's kind of the core of what we're diving into today,
Right.
this whole concept of backpropagation in AI.
Okay.
And we're pulling from this super influential paper from 1986. It's called, get this, Learning Representations by Back-Propagating Errors. Catchy, right?
Yeah.
But seriously, it was published in Nature, so you know it's a big deal.
Absolutely. Huge. This paper, by the way, was authored by Rumelhart, Hinton, and Williams.
Okay.
And it's not just some technical thing. It's like a totally different way of thinking about it.
Okay.
It introduced backpropagation.
Yeah.
And it's an algorithm that's like the foundation
Okay.
for so much of the AI we use every single day.
So hold on. This isn't just some like theoretical thing. This is the stuff that actually powers like AI assistants and like how Netflix tells me what to watch.
Exactly. Is how those things work.
Yeah.
Image recognition, understanding language, even making predictions from like tons of data.
Okay, you've got my attention. But before we get ahead of ourselves, let's break it down a little.
Yeah.
What even is backpropagation?
So at its core,
Because it sounds kind of intimidating, honestly.
it is. Well, it was.
Yeah.
Backpropagation is a solution to a problem. How to get artificial neural networks to learn.
Okay, and just for everyone, quick reminder, these neural networks, they're basically like simplified models of the human brain. Yeah.
That's the idea. Imagine like a network of interconnected units.
Okay.
Kind of like, neurons in the brain.
Yeah.
And each connection between these units, it has a weight.
Weight.
Yeah, like a numerical value.
Okay.
And this value, it determines how much one unit influences the next one. It's like if you're thinking of a signal going from one to the other, the weight's like adjusting the volume knob.
Yeah. Okay, so I'm picturing this right. We've got these connected units.
Yeah.
And how strong those connections are, the weights. That's how the whole network processes, like information coming in.
You've got it. Now, the real trick, the key to making these networks learn is figuring out how to adjust all those weights.
Okay.
So the network spits out the result you want.
Right.
That's where backpropagation comes in.
So to really get how big of a deal this was, let's like break down how it works step by step.
Yeah.
What's going on inside these networks when they get something wrong?
Okay. So picture this. You've got a network.
Yeah.
And it's supposed to, say, identify different types of flowers.
Okay.
It sees a picture of a rose,
Okay.
but it predicts tulip.
It goofed.
Yeah. And this is when backpropagation kicks in.
Okay.
It's like a messenger running back through the network with the news, hey, we messed up.
So it's not just like, oh, wrong answer. It's figuring out where it went off track.
You got it.
Yeah.
Backpropagation goes through every connection.
Okay.
Traces that error back from the output all the way to the input. It's figuring out which of those connections, which weights
Right.
were most responsible for that wrong prediction.
So it's like zeroing in on where the network's thinking went off the rails, so to speak.
That's a good way to put it. And here's the really clever part.
Okay.
Once it's found those connections that caused the error, it adjusts their weights.
So if a connection was partly to blame for the mistake,
Right.
it gets like toned down.
Basically, its weight might be reduced.
Mm-hmm.
And if there's a connection that would push it toward the right answer,
We give that one a boost.
exactly, increase the weight.
So it's like fine-tuning a musical instrument almost. Each tweak of the weights brings the network closer to like the right sound or, well, the correct prediction in this case.
That's a great analogy.
Right.
Yeah. And the whole thing, it's all done with math. There's a function that figures out exactly how much to adjust each weight based on how much it contributed to the error. And you do this over and over again. Tons of iterations, tons of adjustments,
Okay.
and the network just gets better and better at making those predictions.
So it's like the network's learning from its mistakes, just like we do.
Yeah.
But instead of yelling at it, we're like messing with these numbers, these weights.
Right.
So how did Rumelhart, Hinton, and Williams actually show this?
Yeah.
Did they like set loose a network to go identify flowers?
Well, they did, but they were more focused on like basic patterns, you know?
Okay.
One example is really cool. They taught a network to spot mirror symmetry.
Okay.
Imagine you're showing these images to the network. Some are symmetrical, some aren't. And it has to figure out the rule.
Okay, so we're not like giving it the definition from a textbook.
Right.
It's got to learn it by basically trial and error with backpropagation helping it along.
Exactly. And the cool thing is the paper actually shows you a picture of this happening,
Okay.
like a diagram of the network as it's adjusting those weights with each try.
Uh-huh.
you can practically see the aha moment.
Yep.
Like it starts to tell the difference between symmetrical and non-symmetrical patterns,
Yeah.
even with different shapes and sizes.
So it's like it's figuring it out,
Yeah.
even if we don't spell it out.
Right. And that's huge. Just like a kid learning to ride a bike, you don't tell them every little thing about balance.
Right.
This network, it doesn't get rules about what symmetry is. It's figuring those rules out on its own just by looking at examples and tweaking those connections with backpropagation.
That is wild. So if it can learn something as like subtle as symmetry on its own, what else can it do?
That's the question.
Right.
And this paper, it doesn't stop there. They go on to describe how they got a network to understand family relationships.
Family relationships. Now that's a whole other level.
Right.
How do you even begin to teach a computer something so like human?
So they gave the network these representations of family trees,
Okay.
like encoding all the info about who's who and how they're related. And get this, the network didn't just memorize names. It actually built a model in its brain, so to speak, of how families work.
You're saying it could like look at a family tree it's never seen before and be able to tell you who's the grandma, who's the cousin, all that.
Exactly. It's not just about remembering those specific examples. It's about getting those underlying principles.
Wow.
Like the rules of how families are structured.
Yeah.
That ability to generalize, to go from specific examples to bigger ideas, that's what learning really is.
Yeah.
And machines can do it now too, thanks to backpropagation.
Okay, so we've gone from butterflies to like figuring out Aunt Carol's side of the family.
Right. It's a big jump.
This backpropagation thing is clearly a big deal.
Huge.
But for those of us who aren't like coding AI in our basements, what does it actually mean?
Okay, so this is where it gets really practical.
Okay.
But backpropagation is not just some like research project.
Yeah.
It's the engine behind so much of the tech we use every single day.
So like next time Spotify throws some wild song my way that I end up loving, I can thank backpropagation for, broadening my horizons.
Totally. And it's not just fun and games either.
Right.
It's having a huge impact on stuff like medicine,
Okay.
AI systems that can spot diseases way better.
Right.
Or in finance, algorithms making crazy fast trades,
Right.
even tackling climate change, helping us make sense of all that environmental data.
Wow. Okay, so backpropagation isn't just like changing AI, it's changing how we understand what's even possible.
Exactly.
But
Right.
is it like the final answer? Is this how our brains learn too?
That's what's so interesting. The authors actually talk about this in the paper.
Okay.
As amazing as backpropagation is, it's probably not the whole picture.
Okay.
Our brains, they're just so complex.
Right.
We learn from way less data than AI needs right now.
That's true.
And we're better at taking what we learn and applying it to something totally different. And that's something AI still struggles with.
So as cool as backpropagation is, our brains are still holding out on us a little.
For sure. Like, people are really interested in this thing called unsupervised learning,
Okay.
where AI can learn without us having to, spoon feed it labeled data.
Okay.
That's more like how we learn, just by observing.
Right.
And then there's spiking neural networks,
Okay.
trying to mimic how our neurons use timing and stuff.
Wow. So it's kind of humbling, We haven't figured it all out.
It really is.
Yeah.
But that's what's exciting.
Right.
Every discovery just opens up more possibilities.
It makes you think about like the future of AI and what it can solve.
Exactly. Yeah.
Well, as we wrap up our deep dive here,
Yeah.
one thing's for sure, backpropagation, it's a game changer.
Cool.
All this innovation stuff we used to just see in sci-fi, it's here because of this algorithm.
It's incredible.
Shows what we can do when we like really try to understand how things work,
Yeah, absolutely. It's been great talking about this.
Yeah, this was awesome.
Really fascinating stuff.
And to everyone listening, thanks for joining us on this deep dive. Hope you learned something new about backpropagation.
Yeah, for sure.
It really is the like hidden force behind so much of our world now.
It really is.
So next time you're snapping a pic or watching a movie or just like using some new tech, think of backpropagation. It's pretty wild. Until next time, keep asking questions and keep on learning.